we have seen last time that in the plastic region, we have a strain hardening zone, which will follow a linear profile in a log-log graph. Okay, and we have seen that n will represent the slope of this linear variation, and to determine the value of k, since here this is a log scale, so here we represent log of sigma. Okay, so here you have log of sigma, and here you have the scale log of epsilon. Okay, so when epsilon true is equal to 1, you know that the corresponding value of log 1 is 0. Okay, so if you plug in the equation, if we plug in the equation epsilon true equal to 1, we get that log of sigma will be equal to log of k. So from here you can determine this coefficient k. Okay, so this is a first method to find the value of k and n. If you want to have another method without drawing the log-log curve, what you can do is, if we go back to the true curve, okay, true strain stress curve, what we can do is we can take 2 points in the strain hardening zone. So for example, I can just take these 2 points that belong to the strain hardening zone. I should pay attention to have these 2 points between the elastic limit and the start of necking, so that the points belong to the zone required, which is the strain hardening zone. And then I can read the corresponding values of the true strain and true stress for each point. And since these points should satisfy the equation of the flow curve, which is sigma equal to k epsilon n, we can write 2 equations with 2 unknowns, which are k and n. So we will do this together in practice and problems to see how to apply. Just you should know this idea that I have 2 graphical methods to find k and n, or I work on the true stress strain curve with the normal scale, then I take 2 points and I apply the equation sigma equal k epsilon n on each point to get 2 equations with 2 unknowns, which are k and n. The second possibility to find k and n, I draw the log-log graph, and then from the linear variation, I can get the slope equal to n, and to get k, it's corresponding to epsilon true equal to 1. So from here, because in the log-log plot, the strain hardening zone follow a straight line, then the relationship between the true stress and the true strain in the plastic region can be computed as sigma equal to k times epsilon to the power n, where k is the strength coefficient and n is the strain hardening exponent. Okay? Any question until here? Now, we will now see the different categories of stress-strain relationships. The first category is the perfectly elastic scenario. So in this case, the behavior of the material is defined completely by the modulus of elasticity, because this material will not undergo any plastic deformation. It will have rupture before entering the plastic region. So this is in general the property of brittle materials, since fracture takes place instead of yield. So we don't have a yield point and we don't have a plastic region. We only have an elastic region. So this behavior is common for brittle materials as ceramics, many cast irons, and thermosetting polymers. Now, the second type of stress-strain relationships is the elastic and perfectly plastic. What do we mean by this? So this material will undergo, if we put stress on it, it will undergo 2 phases, elastic and plastic. But what is particular for the plastic region is that once it yields, it will not require any additional stress to strain. This means that once I reach the yield point, I can, without increasing any more the stress, I can reach a very high deformation. Okay, So this is a perfectly plastic behavior. In this case, we have for the first region, I need the modulus of elasticity to define it. And once the yield point is reached, the flow curve, this is a particular case of the flow curve. Because you know, in general, the flow curve is of the form sigma equals to k times epsilon to the power n. So we have here, in this particular case, what will happen is that the stress will remain constant in the strain hardening zone. So it's not anymore called strain hardening. It's perfectly plastic because sigma is not increasing. We say it's strain hardening when sigma is increasing to continue the deformation. Okay. So here, since sigma is constant, then the value of n should be 0. Okay. And for this particular case, k will be equal to the yield strength. Okay, so for this type of materials, the flow curve is defined by k equal y and n equal to 0. And the metals that behave like this are metals that are heated to sufficiently high temperature, above the recrystallization temperature. We will define together in this chapter what is the recrystallization temperature. And we will see that in general, when we heat, the properties of the material will change because it will become more ductile and the strength of it will be reduced. Okay, so the behavior of the material is largely affected by its temperature. So for the same material, you can have a simple behavior like strain hardening, the curve we have shown before. But if you heat it to a sufficient high temperature, it will behave as elastic and perfectly flat. Okay. So now the third type is the conventional type we have seen together, which is the elastic and strain hardening behavior. Here, of course, it's a log-log plot. Why you can know directly it's a log-log plot because here it's linear. Okay, if you draw it on a normal scale, you will have a curve. But since we are drawing it on a log-log plot, it will be a straight line. So here you can directly say that this is a log scale. Okay, and in this case, both will be in a log scale, both will be linear. But what is particular for the elastic and the elastic region is sigma, is sigma equal to the modulus of elasticity E times epsilon. So if you apply on it log, what do you will have this log of sigma is equal to, you know that log of A times B is log of A plus log of B. So it's log of E plus log of epsilon. So you can see here that for the elastic region, it's a particular case of the equation of strain hardening because n will be equal to 1. Okay, so for this characteristic, n is equal to 1. Okay, and in this case, if you want to find the corresponding value of k, okay, k will be equal to what? K will be equal to the elasticity modulus. Okay, so this is the elastic region is a particular form of k epsilon n, where n is 1 and k is e. Okay, this is why in a log-log plot it's also a linear variation, but you can see the difference in the slope. Because when you move from the elastic to the plastic region, what will happen to the slope? It will decrease. Because as we have seen last time, it will be easier to deform when I reach the plastic region. Okay? Any question on this? And this behavior is the case for most ductile metals when they are cold worked. So we will see in manufacturing processes, we have cold worked processes and we have hot worked processes. And it's very important to know these characteristics to know how to deal with materials when we are doing a manufacturing process on low temperature, and how will be their behavior if we heat them to a sufficiently high temperature. Now, we have seen together tensile tests, and now we will go over compression tests. We will see that nearly we can take conclusions of compression tests like tension tests, and sometimes we can use the same data as we will see together. Okay, so compression consists on applying a load that squeezes the ends of a cylindrical specimen between two plates. The compression force applied to the test piece will result in a change in height and diameter. So here it is the opposite of tension. So instead of having elongation, you will have reduction of the length of the specimen. And instead of having area reduction, you will have area increase. Okay. Now, let us see the graphs, the engineering graph and the true graph. Just before this is the compression setup. It is the same setup, but the difference is that instead of moving the lower plate to cause elongation, you move the upper one downward, okay? And this will cause the compression of your specimen. Now, for definition of the engineering stress, it's like the case in tension, just here it's a negative value, okay? So sigma, if we just put sigma, it's equal to minus F over A0. But look, if you put sigma compression, and if you put sigma C, then no need to put the sign, because once you put compression, so you know that you are compressing your specimen, so you just put the absolute value. But if you just put sigma, then you should put the negative sign, okay, which is minus F over A0. So this is the definition of the engineering stress, like we did for the tensile test. And of course, we have also a definition for the strain. For the strain also will be negative, because the engineering strain is final height minus the initial height over the initial height. And we know that in compression, the height is reduced. This is why the engineering strain will be negative. Now, as we said before, so since height is reduced during compression, the value of E is negative, but the negative sign is usually ignored when expressing compression strain. So when we say EC, we just put the absolute value, okay? Now, let us look together at the engineering curve. It's clear that the engineering curve is quite different from the in compression test from the case in a tensile test. Why? Who can explain for me why here it's different? Any idea? So what we can see here, we have seen before that the engineering curve represents the variation of the load F, okay? When we do a compression test, since the area is always increasing during the test, then the force needed to continue to increase the strain, okay, will be higher. This is why we don't have in the plastic region a reduction of, if you want, in the case of tensile test, this is the behavior we have. It's like this, and then we have the necking part, okay? First, here we don't have a necking part in compression. Necking is only a property of tension. And plus, since here the area is increasing, we have a difficulty, and we need a higher force to cause this. So the force is continuously increasing. It will not decrease in any stage since no necking behavior. This is why the engineering curve is quite different from the tensile curve. But what is nice is that the true curves are very close. Okay, so it's true that F variation is different, but when you divide F by the actual area, okay, so it's true that F is increasing, but also A is increasing. And the increase of A can overcome, and if you want, can overcomes the increase of F. So sometimes you can have that in the true curve, you will have that the slope will be decreased, okay, for the stress. We will see this in the figure after. So although differences exist between engineering stress-strain curves in tension and compression, the true stress-strain relationships are nearly the same. And since tensile test results are more common, flow curve values K and N can be deduced from tensile test data and can be applied to compression operations. When using tensile K and N for compression, we should ignore necking. Yani we don't have necking in compression. This is the only difference in the true curve, which is a phenomenon that is particular to tensile tests. Okay, so as I told you, the behavior of the engineering curve is different because of the variation in area. The variation in area in tensile test is different, is reduction, while the variation in area in compression test is an increase in area. This is why the variation of F is different. But the variation of the stress, when you divide F by the actual area of the specimen, you will obtain close behavior in tensile and compression tests. This is why you can say that I can generalize results I get from tensile tests to compression tests. So this is feasible, okay? Especially when we talk about ductile materials, not about brittle ones, okay? And sometimes we will, we will not go into these tiny details, but if you have taken in mechanics of materials, you know that, for example, some materials are weaker in tension than compression. This is the case of brittle material, for example. In this case, the curves in the true curves in tension will be different than in compression. But in general, for ductile material, the behavior will be the same in tension and compression. Okay. Now, what about testing of brittle materials? Brittle materials are difficult to test in tension because they cannot, they do rupture. They can easily reach the rupture state. This is why, in general, when we have brittle materials as ceramics, we do a different type of testing. Okay, since they possess elasticity but little or no plasticity. So in this case, conventional tensile tests are not easily applied. This is why we replace the tensile tests by bending tests, and also called flexure tests. It consists on a specimen of rectangular cross-section positioned between two supports, and the load is applied at the center of the section. Let us see here. So you have here a rectangular cross-section supported at the two sides. We apply at its middle a force F. If you have taken the statics course, you know that this force can lead to deflection. Okay, it will lead to deflection of the beam or of the rectangular cross section, and also it will cause compressive stresses from the upper side and tension stresses from the lower side. So the bending test also cause compression and tension, and this is why this test can be used to calculate the to know the behavior of a specimen in tension. Okay, so here we will continue to increase the force until rupture, and in this way we can know the behavior of the brittle material. So for testing of brittle materials, since they deform elastically until fracture, and failure will occur because tensile strengths of the outer fiber of the specimen are exceeded. So by performing this test, we can calculate what is the maximum possible tensile strengths of these materials. And in general, for these materials, the failure type is called cleavage, which is common with ceramics and metals at low temperature, in which separation rather than slip occurs along certain crystallographic planes. So we will have separation in the along fibers of the materials that are subjected to tension. Okay. Any question until here? Now, another behavior that is important for materials is the shear behavior. and we need to know what are the shear properties of a material. A shear test consists of application of stresses in opposite directions on either side of a thin element. So we can see here in the figure, if I have this element and I apply forces in opposite directions, the element will be subjected to shear. And under shear, we will have deformation. Here, the deformation type is change in angles. So you can see here that initially the angles are 90 degrees, for example. Due to shear effect, we will have a variation in angles. Okay, so we can define the shear strain as tangent of this angle, which is delta over b. Okay, so this is a way of defining the shear strain. And of course, for the shear stress is defined as the force applied over the cross-sectional area. So here, if I draw it in 3D here, this will be the area subjected to shear. So to find the shear stress, I should divide F by A, okay? And the shear strain is defined as delta, which is the displacement along the force action, over the distance separating the two forces in the perpendicular direction. So shear stress is defined as tau equal F over A, where F is the applied force and A is the area over which deflection will take place. The shear strain is defined as delta over B, where delta is the deflection of the element and B is the distance over which deflection occurs. Now, concerning the torsion stress strain curve, okay, so typical shear stress strain curve can be done from a torsion test. Okay, so in this case, we will have the variation of shear stress with shear strain. And as you can see here, we can also define two regions. We have an elastic region first, a yield point, and a plastic region. So, but of course, no necking, zone here. We have fracture at a certain point. And at fracture, we can, the shear corresponding is called the shear strength. Okay. Now, to define these regions, we have in the elastic region, we can define a relationship just like in tensile tests. So it is the shear is equal to G times the shear modulus gamma, where, the shear strain gamma, and G is the shear modulus. So instead of the elasticity modulus, we have the shear modulus G. And we have a linear relationship between the shear stress tau and the shear strain gamma. Now, doing experimentation, we have been able to set a relation for between G and shear modulus G and elastic modulus E. And we have observed that for most materials, we have the following relation between the two, that G is equal to 0.4 times E. So if they gave you one of these two and you want to find the other, it's fine to use this relation, okay? Now, the relationship is similar to flow curve for a tensile test. So as we have seen, you have an elastic and a plastic region, but no necking zone. So the shear stress at fracture corresponds to the shear strength. And also we have found a relation between the shear strength and the tensile strength. So we can relate properties. So if I know the tensile strength from a tensile test, I can deduce the the tensile strength by this relation, which is that the shear strength is equal to 0.7 times the tensile strength. Okay. Now, since in torsion processes, we don't have variation in cross-sectional area, so nearly the cross-sectional area is the constant in a torsion test. So no need to have engineering and true curve, because engineering and true curves differ due to variation of cross-sectional area. But in torsion, we don't have this since we don't have a change in cross-sectional area. So we just can say that the engineering stress strain curve for shear is the same as the true stress strain curve for shear. Now, Another important properties of material is hardness. Okay, and the hardness represents the resistance to permanent indentation. So let's say you are applying a certain load on a specimen, and then you remove this load. Indentation is a mark, so we will see it now in an example. If you have a ball that is stressed on if you press a ball on a certain specimen, it will tend to cause a certain indentation. Okay, higher is the permanent indentation side, more will be higher, lower will be the hardness. Okay, so the hardness will is the property resisting permanent indentation. So good hardness in general means that material is resistant to scratching and wear, and it is a very important property for the tools that we use in manufacturing, because you know that these tools will be in contact with the object to deform, and to use it for a long period of time, it should have a high hardness to resist scratching and wear. So most tooling used in manufacturing must be hard to avoid scratch and wear resist and have a wear resistance. Now, concerning hardness tests, we have several tests for hardness, uh, and they are commonly used for assessing the material properties because they are quick and convenient. We have a variety of testing methods that are appropriate due to difference in hardness among different materials. Now, in this course, we will go over mainly the two most well-known hardness tests, which are Brinell and Rockwell. Okay, now we have other methods as Vickers, Knoop, scleroscope, and durometer, but you don't have to know the differences between them because we will mainly focus on the two most common, which are Brinell and Rockwell. Okay, so let us see how these tests are performed. To start with, we have the Brinell hardness test. What is the idea of this test? This test is widely used for testing metals and non-metals of low to medium hardness. So as we have seen, each test will be typical of a certain material. Okay, this is why you have a high variety of tests, because each material will have a suitable test for it. So for Brinell hardness test, we use it in general for metals and non-metals with low or medium hardness. And in this test, a hard ball is pressed into a specimen surface with a load of 500, 1,500, or 3,000 kilograms. Okay? And under the effect of this force, what will happen is we will have a certain indentation shape in the specimen. And the indentation shape in the specimen will have a circular cross section. Okay, so by measuring the circular cross section here, okay, we can come up with a relationship. Okay, the relationship I will give them for you in a sheet, and we will practice on it in examples. Okay, because here in the slides they are not يعني نحن we study the slides of the book. Okay, in the slides they didn't include these formulas, but I prepared a sheet for you for these formulas to know how to so you can use it, of course, in the exam. You don't have to remember anything. I will send you the formula sheet, and we will do examples on it together. Okay, so you have a formula that will correlate the hardness to these properties, to the indentation diameter and the ball diameter and the force applied. Okay, so of course, higher is di, then lower will be the hardness. So because the hardness is the resistance to permanent indentation. Okay. Now, the second type of test is the Rockwell hardness test. It is another widely used test, and it consists on the following. A cone-shaped indenter is pressed into a specimen using a minor load of 10 kilograms, thus seating indenter in material. And then after this step, a major load, which is much higher than 10 kilograms, so for example, 150 kilograms is applied, which will cause the indenter to penetrate beyond its initial position. And this additional penetration distance is converted into a Rockwell hardness reading by the testing machine. So if you want, it's like a scale that we come up with a scale to measure hardness. Okay, which is proportional to in relation with the distance of penetration. Because higher the penetration distance, lower will be the hardness. Okay, so this is a figure showing the setup. So as you can see, in an initial position, we put a minor load. This minor load will cause just a small penetration of the cone in the specimen. Now, after reaching the state, we increase a lot the load, so we put a much higher load, F. Under the effect of F, we will have a further penetration into the material. And higher this penetration is, lower will be the hardness. Okay, and we have a formula that will convert from, will give us the corresponding hardness function of this distance. Okay, so this is the idea of the Rockwell hardness test. Now, as we have seen before, the temperature has a very important effect on materials properties. Okay, and in general, with increases in temperature, as you can see here, we have an increase in ductility. So the material can deform plastically more. It can strain. It can reach higher strains and higher percentage of elongation. On the other hand, the yield strength and the tensile strengths are reduced. Okay, so of course, we have the advantage of increased ductility, and sometimes the decrease of tensile strength is of advantage because the deformation process becomes easier, but is not an advantage for the final product. So we have seen that this has positive and negative effects. So decreasing the strength of the material will have a positive effect on the manufacturing process, which will become easier because we need to apply smaller loads in order to cause the deformation. On the other hand, for the final product, in general, we desire to have a certain tensile strength. So this is why we need to have a compromise between the final properties and the manufacturing process that we are using. Okay. Now, Karim, are you asking about what for inversely proportional? Karim, do you hear
Between
me?
ductility and yield strength.
Yes, of course. The ductility and yield strengths are inversely proportional. Yes. Okay. Because higher is the yield strength, this means that it is harder to deform the material, to strain it. Okay. So ductility will increase when you reduce. They are going with each other. When you increase the temperature, yield will be reduced and ductility will be increased. Okay. Now, what about the hardness? How the hardness is affected by temperature? Also, as expected, okay, the hardness is reduced with temperature. But you have some materials that can, the slope of reduction of hardness is smaller than the others. So, for example, ceramic is hard. Even at high temperature, it will maintain an acceptable hardness. So, if you need to come up with a final product with high hardness, one possible material is ceramic because it can maintain high hardness even at very high temperatures. On the other hand, for example, for steel with low carbon content, you can see that the slope of decrease of hardness is very high with temperature. So as temperature increases, the hardness is reduced dramatically. So you can reach a very low hardness at high temperature. Okay. And now, in case you want to have a final product with higher hardness, what you can do is you can implement to steel a higher percentage of carbon. So you can see here that for high carbon percentage in steel, you can reach better hardness. Okay, so than the low carbon content. So this is the curve for high steel, high carbon steel, and also we have much alloys of steel. And by implementing other components to steel, you can reach a much higher hardness. Okay, so this is the importance of creating alloys or of combining several materials together, because you can play with the properties in this way. Okay, so if you desire to have a higher hardness, you can prepare alloys that will give you better properties. Okay, or if you increase the percentage of carbon, also it can increase the hardness of steel. So always you should know what is the property desired to know what are the strategies to do. Now, we said that we will define the recrystallization process. Okay, what is the recrystallization process? We know that most metals strain harden at room temperature according to a certain flow curve with N positive. Okay, so if you remember, when we have seen the different behaviors, we have seen that when if a certain metal, when it is manufactured at cold temperature, if we draw its stress strain curve, we will have a flow curve characterized by sigma equal k epsilon to the power n. However, if we heat to a very high, sufficiently high temperature, the behavior will become perfectly plastic. This means what? This means that n will become equal to 0. So once we reach yield, we don't need to increase any more the stress to strain the material. This process is possible by reaching the recrystallization temperature. Now, what do we mean by this? Okay, if we heat sufficiently to a high temperature, strain hardening will not occur. Why? Because new grains will form that are free of strain, so they can strain easily without need to increase the stress. This is called the recrystallization process. Okay, so whenever we heat to a certain temperature for which we will start to see in the metal grain formation of small grains, and these small grains will allow easy deformation because they can slide, if you want, easily with respect to each other. Okay, so the metal in this case behaves as a perfectly plastic material for which the exponent n of strain hardening will be 0. Okay, and in this case k, the coefficient k will be equal to the yield strength. Okay, now what is the definition of recrystallization temperature? Recrystallization temperature of a given metal is about 1/2 of its melting point, and it's measured on an absolute temperature scale. So in general, we reach recrystallization temperature before melting, okay, half of melting, because we are still in the solid state, but we will have formation of grains that are not, if you want, very attracted in a very solid way, as is the case for cold temperature. Okay, so in this case, it will be easier to deform the material. Now, recrystallization process takes time. This is why we decided on a definition of recrystallization temperature, which is specified as the temperature at which new grains are formed in about 1 hour. So we should wait 1 hour before starting to see the formation of grains. Okay. Now, what about fluid properties that are desired in manufacture? Okay. So we know that the fluid behavior, okay, is desired in many manufacturing processes. Why? Because fluids can take the shape of the containers that hold them, and many manufacturing processes are accomplished on materials converted from solid to liquid by heat. For example, you have, this is the case of casting. Okay, so these processes are called solidification processes, and we will see these processes in details in the coming chapters. Okay, and many examples of solidification processes are given here. We have metals that are cast in molten state. You have glass that is formed in a heated and fluid state, and the majority of polymers are shaped as fluids. Okay, so I will open a new session to continue. Okay, I will open a new session.